What if I told you that right now, at this very moment, there's another version of you making a completely different decision? Not in some fantasy world, but in an actual, physical universe that exists parallel to ours. Before we get started, check out the link in the description to download our ebook. For decades, the multiverse has been dismissed as science fiction, the stuff of comic books and Hollywood blockbusters. But something just changed. Scientists have found something in the data that shouldn't be there. An anomaly so strange, so perfectly unexplainable by our current understanding of physics, that it's forcing even the most skeptical researchers to ask a question they never thought they'd seriously consider. Could this be the first real evidence that we're not alone? Not in our universe, but among an infinite sea of universes. Let's rewind for a moment. To understand why this discovery is so mind-bending, we need to talk about what we actually mean when we say multiverse, because this isn't just about parallel Earths where you're a superhero or where dinosaurs never went extinct. The scientific concept of the multiverse is far stranger and far more profound than that. Think about the universe as we know it. Everything you can see, everything that exists, every galaxy, every star, every atom, all contained within the boundaries of our observable universe. About 13.8 billion years ago, the Big Bang happened. Space itself began expanding, and it's been expanding ever since. But here's where it gets interesting. In the first fraction of a second after the Big Bang, something called cosmic inflation occurred. The universe didn't just expand, it exploded outward faster than the speed of light, growing from smaller than an atom to larger than a galaxy in less time than it takes light to cross a single proton. This inflation solved a lot of problems in cosmology. It explained why the universe looks so uniform in every direction, why it's so flat, why certain particles we predicted don't actually show up. But inflation also created a new problem, or perhaps an opportunity. According to the math, once inflation starts in one region of space, it might never fully stop everywhere. It could keep creating new bubble universes, each with its own Big Bang, each with potentially different laws of physics, different constants, different versions of reality. Some universes might have stronger gravity, others might have no stars at all, and in some, the conditions might be just right for complexity, for chemistry, for life, for consciousness. This is the multiverse. Not a fantasy, but a serious prediction that falls naturally out of our best theories about the early universe. The problem, we've never had any way to test it. If these other universes are separated from ours by vast gulfs of inflating space, forever beyond our reach, how could we possibly know they're real? How could we ever find evidence? That question seemed unanswerable, until now, in early 2025. A team of cosmologists, analyzing data from the most precise measurements ever made of the cosmic microwave background, found something extraordinary. The cosmic microwave background, or CMB, is the afterglow of the Big Bang itself. It's light that's been traveling through space for over 13 billion years. And it carries with it a snapshot of what the universe looked like when it was just 380,000 years old. Scientists study this ancient light, like archaeologists study fossils, looking for clues about the universe's birth and evolution. The CMB should be almost perfectly smooth. Almost there should be tiny temperature fluctuations, little ripples that eventually grew into galaxies and stars and everything we see today. And for decades, that's exactly what we've observed. The fluctuations match our predictions almost perfectly. But this new analysis revealed something that doesn't match. A pattern, a specific configuration of hot and cold spots arranged in a way that our standard models can't explain. It's not random noise. It's not instrumental error. The team checked and rechecked their calibrations, ran thousands of simulations, even analyzed data from completely different satellites. The pattern is real. And it looks exactly like what theoretical physicists predicted we might see if another universe, another bubble in the cosmic foam, had collided with ours during the first moments of inflation. Imagine two soap bubbles merging. Where they touch, they leave a mark, a circular pattern on each bubble's surface. If another universe bumped into ours billions of years ago, it would have left a similar imprint, a vast circular pattern stamped into the fabric of space-time itself. And that pattern would still be visible today in the cosmic microwave background, like a cosmic bruise that never fully healed. The mathematics are elegant but unforgiving. The signal they found matches the theoretical predictions with startling precision. The The size is right, the temperature difference is right, even the polarization of the light, the way it's oriented in space, matches what a collision would produce. It's not definitive proof, not yet. But it's the first time we've ever seen anything in observational data that could plausibly point to the existence of another universe. When the paper was first circulated among cosmologists, the reaction was a mixture of excitement and deep skepticism. This is how science should work. Extraordinary claims require extraordinary evidence, and the scientific community immediately began the process of trying to tear the findings apart. Some researchers pointed out that we've seen anomalies before. The CMB has a few features that don't perfectly match our models, and in the past, these have turned out to be statistical flukes or subtle systematic errors. Others noted that the signal, while intriguing, is only at about the 3 sigma level of statistical significance. In particle physics, you need 5 sigma to claim a discovery. 3 sigma means there's still a 1 in several hundred chance this is just a coincidence. But other scientists found the results compelling precisely because they're not too good to be true. If this were fabricated, or the result of wishful thinking, you'd expect a perfect 5 sigma detection. Instead, what we have is tentative, preliminary, exactly what you'd expect from a real but subtle effect at the very edge of our detection capabilities. Theoretical physicists have been more optimistic. For them, this discovery, if it holds up, represents the first observational evidence for a framework that's been developed over decades. It would mean that eternal inflation isn't just mathematically possible, but physically real. It would mean the multiverse isn't speculation, it's geography. Several independent teams are now reanalyzing the data using different techniques. New observations from next-generation telescopes are being planned. If this signal is real, we should be able to find more evidence. Perhaps additional collision signatures in other parts of the sky. Perhaps subtle patterns in the distribution of galaxies that trace back to these primordial impacts. The next few years will be crucial. If this discovery is confirmed, if we're truly seeing evidence of another universe, the implications are almost impossible to overstate. This isn't just another planet or another galaxy. This is another entire reality, with its own space, its own time, possibly its own laws of physics. And if there's one other universe, the theory predicts there should be infinitely many. This changes everything about how we think of our place in existence. For centuries, each new discovery has made us smaller. We're not at the center of the solar system. Our sun is just one of hundreds of billions of stars. Our galaxy is one of trillions. But we could still say, at least we're in the universe. At least this is all there is. Now even that comfort is stripped away. We might be just one bubble among an infinite foam of possibilities. But here's where it gets philosophically fascinating. In an infinite multiverse, where every possible configuration of matter and energy exists somewhere, everything that can happen does happen. Every choice, every chance event, every roll of the cosmic dice plays out somewhere. There are universes where you made different decisions, universes where historical events unfolded differently, universes where the laws of physics make life impossible, and universes teeming with forms of complexity we can't even imagine. Some physicists find this idea liberating. It means our universe isn't special, but that's okay. We don't need to be special to be real, to matter, to experience this remarkable phenomenon called consciousness. Others find it troubling. If everything happens somewhere, does anything really matter? Does probability even mean what we think it means? And there are practical implications too. If we can detect evidence of other universes, maybe someday we can learn more about them. We can't travel there. The laws of physics seem to forbid that, absolutely. But we might be able to read their signatures, study their properties, understand how the fundamental constants and laws vary across the multiverse. This could finally answer one of the deepest questions in physics. Why is our universe the way it is? Why these particular forces, these specific particle masses, these exact values for constants like the speed of light or the strength of gravity? The answer might simply be that all possible values exist somewhere, and we find ourselves in a universe with these values because these are the values that allow for stars, planets, chemistry, and ultimately beings capable of asking the question. It's called the anthropic principle, and while it sounds circular in the context of a real physical multiverse, it becomes a legitimate scientific explanation. So where does this leave us? Standing on the edge of something profound? We have a signal in the data that shouldn't be there. We have a theoretical framework that's been waiting decades for observational support. We have the tools to test this hypothesis in ways we never could before. And we have a question that, if answered, will fundamentally reshape our understanding of reality itself. This is science at its most thrilling. Not because we have all the answers, but because we might be asking the right questions for the first time. Whether this particular detection holds up or not, the search for the multiverse has moved from philosophy to physics, from speculation to observation. We're no longer just imagining other universes, we're looking for them. And maybe, just maybe, we found one. So tonight, when you look up at the stars, remember that you might be seeing only the tiniest fraction of what exists. Beyond the edge of our cosmic horizon, beyond the reach of any telescope, there might be an endless ocean of worlds, some empty and lifeless, others teeming with wonders we'll never witness. And in at least one of them, if the mathematics is right, another version of you is looking up at their sky, wondering the same thing. Are we alone in the universe? The answer might be no, but not in the way anyone expected.